Hello everyone, I'm Debbie and I'm here with my teammates LaShonda, Alex, and Tatya, and we're working group 1. We're here to talk about hypothesis testing. Hypothesis testing is a way to test a hypothesis about a population with data taken from a random sample. The first thing we need to do is state our null hypothesis, which is usually written H0. The null hypothesis is a statement about the population parameters or model that we are testing. This is what we are going to believe unless we have enough data to reject it. The claim that we are testing against this is called the alternative hypothesis, which is usually written H1 or HA. It is important to remember that the null hypothesis and alternative hypothesis are statements about a population parameter or model, not a statement about our data. Let's look at an example that we adapted from the book Introduction to the Practice of Statistics by Moore, McCabe, and Craig. According to the records of a student loan provider, the average credit card debt of student loan applicants in the Midwest is $3,260, while student applicants in the West had an average credit card debt of $3,817. Can we conclude from this that the average credit card debt of student loan applicants in these two regions is different at a significance level of 5%? So our null hypothesis is the statement that we are testing, that there is no difference in the true means. It is important to understand that we are not proving the null hypothesis. We are determining whether we have enough evidence to disprove it. If we decide that we don't have enough evidence to disprove it, that doesn't mean that we are confirming it, just that we don't have enough data to reject it. Future studies with more data may be warranted. One important decision that we have to make about our alternative hypothesis is whether it should be one-sided or two-sided. A one-sided test is only appropriate when we know whether we expect the true parameter to be higher or lower from the value in the null hypothesis. And this is a decision that we should make without using the data. In this case, we don't know whether we expect credit card debt to be higher in the Midwest or the West, so a two-sided test is appropriate. Unless you have a really good reason for using a one-sided test, you will normally use a two-sided test. So in this case, our alternative hypothesis is that the true means are different. The level of proof that we need to reject the null hypothesis is called a significance level. If we were to choose a significance level of 10%, we are saying that we want our data to be conclusive enough that if the null hypothesis were true, we would only get data this far from our null hypothesis 10% of the time. If we reject our null hypothesis when it is actually true, this is called a type 1 error. Our significance level is the probability that a type 1 error will occur. If we fail to reject our null hypothesis when it is actually false, this is called a type 2 error. 1 minus the probability of a type 2 error occurring is called the power of the test. The way we measure how far our data is from the null hypothesis is by calculating a test statistic. Now my teammate LaShonda is going to talk about test statistics.
There are several test statistics one can use, but for this particular example, we're given that there are two normally distributed but independent populations and the standard deviation is known. So we're going to be using a z-test for comparing two means. With that we have z is equal to x bar 1 minus x bar 2 minus delta divided by the square root of sigma squared 1 divided by n1 plus sigma 2 squared divided by n2. We have z equal to the estimate minus the hypothesis divided by the standard deviation of the estimate. From the problem, we know that this equals z. This is equal to 557 minus 0 divided by 375. This will give us a z-score of 1.49. I'm going to pass it to Tatya for further analysis.
We can figure out our p-value by first looking at the rejection region. And since this is a two-sided test, the rejection region will be on both sides of the normal distribution curve. So it will be on this side and on this side. And here is the test statistic. And so we need to figure out the area here and the area here. And we can figure it out by looking at the normal distribution table. 1.49 is 0.9319. So the area from here to here is 0.9. So this area is going to be 1 minus 0.9319. And so since the normal distribution curve is symmetric, then this area is the same as this area. So our p-value will be 2 times 1 minus 0.9319, which will be 0.1362. And assuming an alpha of 0.05, then our p-value is greater than alpha, which means we fail to reject our null hypothesis. And so we can conclude that we do not have enough evidence to show that the average credit card debt of student loan applicants in these two regions is different. And now I will pass on to my teammates Alex to talk about the use and abuse of the hypothesis.
All right, I'm going to talk about the use and abuse of tests. Using tests wisely are not so simple. Certain tests are only valid under certain circumstances, and there are many variables to consider when determining the parameters of a test. You should hesitate when determining when to use a correct significant test based on the context of what your hypothesis is. Today I'm going to talk about choosing a level of significance, the fact that statistical significance doesn't necessarily imply practical significance, and on the other hand, the lack of statistical significance doesn't necessarily imply the lack of practical significance. On the subject of choosing a level of significance, the purpose of a hypothesis test is to give a quantitative degree of evidence provided by the sample against the null hypothesis. A measure of evidence is given by the p-value. So generally, if p is less than 0.05, it is statistically significant. But that's an arbitrary number. There's no sharp border between statistically significant and not statistically significant. There's only increasing evidence against the null hypothesis as p decreases. You have to consider the context of your problem when you basically choose a level of significance for your test, you know? Because different problems in different fields will have different levels of significance that will be statistically significant. What statistical significance doesn't mean is that it doesn't necessarily imply practical significance. Rejecting the null hypothesis implies that there's good evidence from the sample that an effect is present. However, this effect can be very small. Just because you have some kind of statistically significant effect on your hypothesis doesn't necessarily mean it's practically, like, it might not mean anything. So essentially it tells us there's a difference, but it doesn't necessarily measure the degree of importance of this difference. When drawing conclusions based on statistics, again, consider the context of the experiment. All right, so you also don't want to ignore the lack of statistical significance. Over here I said the lack of statistical significance doesn't necessarily imply the lack of practical significance. Just because a p-value doesn't necessarily attain a given level of significance doesn't mean that it's not. Right, so lack of statistical significance doesn't necessarily mean lack of practical significance. In one example, a medical group did a hypothesis test on HIV transmission. And although the test proved to be lacking in statistical significance, we can see from the results that the practical significance were pretty major. So they recorded this based on incidence ratios. They had a bunch of incidence ratios, which were the new level of transmission of HIV under a new medical procedure over the old level of transmission. That means if the incidence ratio is 1, there's no difference, right? Under a 5% level of significance, so alpha is equal to 0.05, the 95% confidence interval was 0.63 and 1.58. That's equal to a 37% decrease in infection and a 58% increase in infection. Anything outside of these bounds were considered statistically significant. But as you can see, 37% decrease and 58% increase is actually a big practical significance in the medical field. So just because something has a lack of statistical significance doesn't necessarily mean that it's lacking practical significance. In conclusion, small effects can be very practically significant, and lack of significance doesn't necessarily imply that the null hypothesis is true. There's a disconnect between statistical and practical significance, so you have to be careful and consider the context of your experiment when determining what hypothesis test to use. We are Working Group 1, and thank you for watching.